Okay. So I had you guys watching the Newton's second law stuff, even though we hadn't finished completely the Newton's first law stuff from the other day. So what I'm going to do is finish that up, and then we'll go back to Newton's second law. Luckily, the two don't really depend on each other all that much. Okay, they're kind of two different ideas, but we will finish up the Newton's first law stuff, and then move back to Newton's second law. We'll start looking at like Newton's second law in systems. That would be interconnected objects. Okay, yesterday, you guys probably just got to like the elevator type questions and things like that, right? Okay. So Newton's first law, okay, states as follows. An object at rest will remain at rest. An object traveling at a constant, it should say velocity, not speed, will continue to do so unless acted upon by a net force. Now, why is it important that I say this should say velocity and not speed? Yeah, it needs to be going the same direction. Here's the weird thing. An object can travel at a constant speed and not a constant velocity at the same time. That means the magnitude of how fast it's going, okay, doesn't change, but the direction does, right? Prime example of that, anything moving in a circle, right? So if I just like put something on the end of a string and whirl it around in the air, it's traveling at a constant speed, but it's always accelerating because its velocity is always changing. Its direction is always changing in order to stay in a circle. Okay, so that's kind of why that should say velocity. Okay, if something's velocity is changing, it's accelerating, whether even if that's just a change in direction. Okay, so Newton's first law says an object has to be at rest and remain at rest, or traveling at a constant velocity, and it will continue to do so unless acted upon by a net force. Okay, which is why it would be possible to do what you see in the picture on the right here. Okay, if you took a stack of like checkers or poker chips or something like that, and you stacked them up, and then you flipped one at the bottom of the stack, it would be possible to knock out the bottom chip and not have the stack fall over. Okay? Because the rest of the stack isn't having a force acting on it, only the bottom chip. So it would be possible to knock it out, okay, and then not have the stack fall. The same thing is used by someone who's trying to pull a tablecloth out from underneath a bunch of dishes on a table. You've never seen that? Most people screw that up horribly. Okay? It's actually, if you have the right stuff, like not a cloth tablecloth, if you have like that cheap dollar store ones that are like vinyl and really slippery, it's much easier to do it with those than it is with like the cotton tablecloth we use for Thanksgiving. Don't try this on the weekend, okay? Like mom's best china on the table, okay?
I do it with the Tarvel RV stuff we have.
Yes, like the plastic RV stuff, yeah, that'd be fun, yeah. Okay? Well, I'm speaking for myself, I would do it, but so here's essentially how most people screw that trick up. They grab the tablecloth and they pull like this, and they pull like up and towards themselves. Well, what does that do to the tablecloth? It lifts it up, and everything that's on the tablecloth falls over. Okay? The key to doing that right is actually to push the tablecloth against the edge of the table and rip downwards quickly. Because then the tablecloth that's still on the table moves perfectly horizontal and slides right out from underneath the dishes because of Newton's first law. It's slippery enough that it doesn't exert a force on the dishes, and the dishes have enough inertia that they stay put, and the tablecloth slides out from underneath. Okay? The same would be true if you're just trying to get a piece of paper out from under a heavy object. Okay? If you pull it really slowly, the object will move with it. Okay? But if you give it just a quick jerk, out it comes. Okay? This is also the same principle that's used to tear toilet paper. Next time you're on the can, think about this. Okay? I know this is weird and gross, but okay. Next time you're on the can. Okay? If you have a full roll of toilet paper and you just want to rip off one little piece, you can just like that and it rips right off. Okay? Because there's still lots of toilet paper on the roll. So there's a fair amount of inertia for the whole roll to stay put. Try that when it's just about to the end. Okay? When there's just a little bit left, you try that, the whole roll will just unroll. Okay? Because there's not enough inertia with the mass of the toilet paper left on the roll for you to achieve that effectively. Now you have something to do while you're sitting there. All right. So a couple of things to remember. First law uses the phrase net force. Okay? Net means like when I take all the forces into account, there's something left over, okay? If there is a net force, then there's something that's not balanced, and then as a result, there's going to be an acceleration, okay? In Newton's first law, all the situations that it governs have no net force. So in other words, all of the forces are balanced, okay? And there's a net force of 0. Anytime there is a net force, which is what you learned yesterday about Newton's second law, an acceleration will occur. Okay, moving on here. Okay, so a net force can cause a bicycle to pick up speed quickly, but if that same net force is applied to a freight train, any resulting change in motion is nearly imperceptible. Okay, so we say the train has more inertia than the bike because the train has more mass than the bike. Okay, that was the toilet paper little thing I was just telling you about a minute ago. All right, now we were talking about how this is important for like car safety. Okay, we were saying that mass was the most important safety feature your car can have, okay, because it means you have lots of inertia and your velocity is less likely to change than it would be for something smaller. Okay, everyone with me on that? All right, so I'm going to show you some crash videos. Okay, so you can see kind of what nobody gets hurt. They're like the testing videos. Actually, I shouldn't say that. I'm going to show you one that my cousin was in. Okay, it's dash cam footage of her getting absolutely teed up. Okay, she actually broke her pelvis and was in the hospital for like a really long time. But you can see the effect of like bigger mass on a smaller vehicle. Okay. All right, so okay, so now that we've seen those, we kind of get an idea kind of how Newton's first law works. Your mass is important, obviously, okay? It affects your acceleration, okay? And shape of the car, ability of the car to change shape, all of that kind of stuff also affects how much acceleration you experience. Smaller cars with less areas for crumple zones and stuff like that are not going to do as good a job. Now, I mean, we rag on the smart car bit here, okay? And if you're using it to drive on, you know, Deerfoot at 120 all the time, you're not really using it for what it's designed for, okay? The smart car was never meant to drive on Highway 2 at 120 plus kilometers an hour. That's not what it was built for. It was built for stop and go traffic, 60 kilometers an hour, 70 kilometers an hour max. It does a fine job, okay, at those speeds of doing its job and doing a reasonable job in a collision. It was never designed for high speed impact.
Like in the UK, are like 14-year-old like allowed to drive that with their learner's license?
I have no idea what the laws are in the UK.
Sure, there's something like that.
I know there's a lot of scooters driven at that age, but I don't know about a smart car. Mopeds.
That's the sort of thing over here, right?
Well, there are.
Can you track with pedal lawners over here?
I think so. Yeah.
So, no.
Yeah, you can drive a scooter on the learners because the scooter can only go 60, right? Maximum speed. It's their top speed limit.
Basically a bike.
Yeah. Basically. Yeah. Except you got some help going uphill. All right. Okay, so we're looking at that. So remember, quantitatively, inertia of an object is measured by its mass. Okay, so the train has a larger mass, thus it has more inertia. Okay, that's what we're looking at there. Now, here's how your seatbelt works. Okay, all safety devices in your car are also dependent on Newton's first law in order to function, because it doesn't then depend on a sensor, well, sort of a sensor, but not on like an electronic decision-making kind of thing. Okay. Seatbelts work with this mechanism. So you have the ratcheted wheel, okay, that your seatbelt rolls onto each time, right? If you're in a hurry, that's the thing that always catches when you're in a hurry. You yank the seatbelt and you can't get it, and you know you have to back it up to let it go, but you're in too much of a hurry. That thing, okay? So when it locks, what's happened is you've jiggled the mechanism to the point where the locking bar has gone into place. Okay? The locking bar is supposed to go into place if there's a rapid deceleration of the car, okay? Because there's a pendulum underneath the locking bar. Okay? If you're traveling at a constant speed, the pendulum hangs down. If you're accelerating forwards, the pendulum goes backwards and it doesn't have any effect on the locking bar's position. But if you suddenly decelerate rapidly, the pendulum obeys Newton's first law and swings forwards. And when it swings forwards, it pivots the locking bar into the ratcheted wheel. And now the ratcheted wheel can't unroll. So your seatbelt can't come out now. That's what locks the seatbelt into place. Okay? It's a simple mechanism that cannot fail because it is relying on Newton's first law. okay? Your airbags now also rely on Newton's first law, okay? Early airbags were actually triggered by a contact switch, which meant in the bumper, there was a switch that was spaced apart. So if something hit the front of your car and squished the bumper, okay, the two parts of the switch would connect, close the circuit, and detonate the airbag. Problem was is that you could detonate that just by hitting the bumper. Okay? There's actually a video of this guy like sitting at a crosswalk, and there's this old lady with a walker. She's taking forever to go across, and she's an old lady with a walker. He's honking at it. And she finally just loses it, takes her purse and swings it at the bumper and detonates the airbag in his face. Karma. Okay? Total instant karma. But that's obviously not the way we want that sensor to work. Okay? We don't want it to be in contact. I mean, that means that if you're one of those people that can't park, you know, like I see all the time, and they bump into stuff, like if you bumped into the light standard in the parking lot, you blow up your airbag, even though you're in absolutely no danger whatsoever, okay? The airbag would go off. So they instead started using the same device that your phone uses to tell it which way it's oriented. It's called a gyro, okay? And so basically it's just a ball made of conductive material, metal, okay, in a wire cage. And so as you move it around, it touches different parts and it's spring-loaded. Okay? So inside your car, there's a sensor for the airbag that's got this spring-loaded metal ball inside a cage. Okay? If you get hit from the back, from the front, from the sides, the metal ball touches the wires, triggers the explosion. Okay? That detonates your airbags. Right? But it relies again on Newton's first law. It stays on those springs in position unless your car experiences enough of an acceleration to require the airbags. Okay? Which is why in some accidents, your airbag doesn't go off. Okay? The one that I was in, my airbags didn't go off because we didn't accelerate enough to trigger them. Okay? The car that turned in front of us did. Okay? They experienced a much greater acceleration. Their airbags did detonate. Everyone kind of follow me on that? So it uses Newton's first law. It holds, it hangs in place. If you experience a rapid deceleration, ball moves forward, touches the wires, completes the circuit, boom, airbags go off. Okay? You get hit from the side, ball goes the other way, hits the wires on that side, detonates the side airbags, detonates the back airbags, you get hit from the back. Okay? Like, so all of your curtain airbags are triggered by different parts. Okay? You get in a really big crash and they just all go off. Okay? All right. Making sense? So applications, uses of Newton's first law. Okay? All right. Okay. So we're going to skip now to Newton's second law. Okay, so you guys got to the elevator questions yesterday, right? So you did the bobsled one? Okay, and did you guys do this one?
Yeah.
The elevator one? Okay. Did you do the chain hoist?
Yeah.
Okay, so you guys got to differential acceleration then. Okay, so we don't do a lot of differential acceleration type problems, okay? But it's still important to recognize how they work, okay? Calculating net force can be done two ways, and you learned this yesterday. Taking mass times acceleration, or the vector sum of all forces. Okay, those are the two ways to calculate net force. So, for a question like the elevator, okay, or the chain hoist, what I'm really looking at is this. Net force equals mass times acceleration, which equals the mass of the engine times the acceleration of the hoist plus the mass of the engine times the acceleration due to gravity. Okay? Because every individual force can be calculated by taking the mass and multiplying by the acceleration that force would produce. Okay? Sorry, this is also the mass of the engine over here. Okay, so I've got ME times A equals ME times AH plus ME times G. What is in every term? M. Yeah. The mass of the engine is in every one of these terms. In math, if you have the same variable in every term, its effect is the same on every turn. What can you do with it? You can take it out. Okay? So essentially, what we're saying here is it's no longer the net force, it's the net acceleration equals the acceleration that the hoist could produce plus the acceleration due to gravity. Okay? Now, this is important because I'm looking for the mass in this question. Okay? I don't have it. So I cancel it. Now you might be thinking, wait a minute, that's what you're looking for. Why did you get rid of it? I'll show you in a minute why I got rid of it. Okay? So the acceleration of the engine is 1.5 meters per second squared up. That's my net acceleration. That's what's happening. It is the result of the hoist and gravity working against each other. Okay? So I know that this number, A net, okay, my net acceleration is 1.5 meters per second squared, and I'm going to say that's positive because it's up. Okay? What's G? 9.81. All right, so I also know that. Can I find the acceleration that the hoist produces alone? I can. Okay, so I'm going to say the acceleration of the hoist equals the net acceleration minus the acceleration due to gravity. Okay. So that will be positive 1.5 minus negative 9.81. Okay, so the hoist, if it was all by itself, in the absence of any other forces, could produce an acceleration of 11.31 meters per second squared. Okay? Now, why is that going to be valuable for me? Because it tells me the force that the hoist is producing. Okay? And here, I know that the force the hoist produces is equal to the mass of the engine times the acceleration of the hoist. I now have the acceleration of the hoist, and I know the force the hoist can produce. So I can now find that thing I was missing that I was asked to find, the mass of the engine. Okay? So now that I have the acceleration of the hoist, okay, 11.31 meters per second squared, okay, that's the acceleration of the hoist. Now I can say, okay, that the force of the hoist, which is 2.85 times 10 to the 3 newtons, okay, equals the mass of the engine times the acceleration of the hoist, 11.31. Okay, now I can solve for the mass of the engine. Just divide the acceleration over, I've got the mass of the engine. Okay, like I said, we don't encounter these very often, right? But when you do, they're almost always an elevator question. Okay? This is still an elevator. Okay? Something lifting something straight upwards, always an elevator. Okay, did you guys do the skydiver questions? Yeah. All right. So this is an elevator question. Even though the skydiver is falling, it's still an elevator. They're moving vertically. There are two forces. Okay, there's the force of gravity, so they've drawn the free body diagram for you, force of gravity here, and the force of air resistance, or friction, that's acting upwards. All right, so they tell us the acceleration of the skydiver, and they tell us the force of friction, or air resistance. Okay, we want to calculate the mass of the skydiver, so it's essentially the same as what we just did, okay, with the hoist. So our givens are gravity, okay, the net acceleration, okay, and, oh, sorry, that's down, not up. And we're looking for the mass of the skydiver, and we know the force of friction. And it's up. All right, I'll give you a couple minutes to see if you can get that one. All right, so our free body diagram, which is like our givens in a Newton's second law question, is already drawn for us. Picture of the skydiver showing the force of air resistance, friction acting up, and force of gravity pulling down. Okay. We know the net acceleration, and we know the acceleration due to gravity. We're looking for the mass of the skydiver, so it sets up just like the hoist question. Okay, F net equals mass times the acceleration net. Okay, and that's going to equal mass times the acceleration due to friction plus mass times the acceleration due to gravity. Since mass of the skydiver's in every one of those terms, we can cancel it off and do a differential acceleration type problem, right? I need to find the acceleration due to the force of friction, okay? And then I can go from there using the force of friction to calculate his mass. So I'm going to isolate the acceleration due to friction by simply subtracting gravity over to the other side. So that'll be the net acceleration minus the acceleration due to gravity. Okay, and so that will be, okay, acceleration due to friction will be negative 5.96, okay, meters per second squared, because that's what he's actually doing, minus negative 9.81, the acceleration due to gravity. Okay, so we got negative 5.96 minus negative 9.81. All right, so the acceleration that's produced by the force of air resistance or friction is 3.85 meters per second squared up. Now that I know that, I can go back to this. The force of friction equals the mass of the skydiver times the acceleration due to friction. I already know this number is 250 newtons, and I now calculated this number to be 3.85, so now I can calculate the mass of the skydiver by dividing both sides by the acceleration I just calculated. So we'll have 250 newtons divided by 3.85 meters per second squared. So kilogram meters per second squared divided by meters per second squared. We're leaving with kilograms. That's the units for mass. So 250 divided by our answer gives me the skydiver's mass to be 65 kilograms. Okay. Are you all right with that? All right, I'm going to give you a little break here. Okay, so with number one, it says I have this 55 kilogram female bungee jumper who fastens one end of the cord made of elastic material to her ankle and the other end to a bridge. Yep, that's generally how it's done. Okay, that's generally how bungee jumping is done. You want to definitely tie both ends. I mean, it's safer that way. Then she jumps off the bridge. Okay, as the cord is stretching, it exerts an elastic force directed up on her. Okay, that's good. That's what you want to do, because it has to counteract gravity. Otherwise, it's flat. Okay. Calculate her acceleration the instant the cord exerts an elastic force of 825 newtons up on her. Okay. We know her mass, 55 kilograms. Okay. We know the force of the bungee cord. So I'm going to just draw a free body diagram. 55 kilograms. Okay, this is the force upwards of the bungee cord. It's 825 newtons. What force is that? No, sorry. What force is this arrow? Gravity. Yeah, this is the force of gravity. Can I calculate that? Yeah, I have her mass and gravity's 9.81. So yes, I can definitely calculate that. Okay, m times g. So we'll take our 55 times 9.81, right? And we have 539.55. Newtons. Okay. What can I calculate right now? Net force. Yeah, net force is the vector sum of all forces. And it's m times a. Well, they want to know the acceleration, so I'm going to say right now, okay, F net equals m times a, which equals, okay, the force of the bungee cord plus the force of gravity, right? I'm looking for acceleration here, so what do I do with mass? divided over to the other side. Okay, so I'm going to have the acceleration of the bungee jumper being my net force, these two forces added together, so 825 plus negative 539.55 divided by the mass, F net over M. Okay, that's what I'm calculating here in order to get the acceleration of the bungee jumper. Okay, so there's my net force. It's 285.45 newtons up. That's good. I want my net force to be up in this situation. And now I'm going to divide that by her mass, 55. All right, so her acceleration upwards is 5.19 meters per second squared. We only have two significant digits here, so we're going to say 5.2 meters per second squared up. Okay, is that an elevator question? It is. Okay, anytime you have something that is only moving in the vertical plane, okay, and gravity is one of the forces acting on it in the vertical plane, it's an elevator. All elevator questions work the same. Upward forces plus downward forces give you the net force. All right, now, question number 2. During that bungee jump, the velocity of the woman at the lowest point is 0. Not because she hits the ground, but because at that point she's been slowing down because the bungee cord has been pulling up and actually accelerating her at somewhere around 5.2 meters per second squared upwards for some time. Okay, so it's just like when I throw something up in the air. It accelerates downwards the whole time, comes to a stop, and then falls back down. A bungee jump is the exact opposite. I'm falling down, and something's pulling me up. And then eventually I start moving back up again. Okay, hopefully. Okay. And then I kind of bob up and down for a little while until they lower me down, or pull me back up. Usually they lower you down. Okay. All right, so compare the direction of her acceleration at the lowest point of the jump to the part of the jump where she's accelerating due to gravity. Okay, so when she's in free fall, her acceleration is up or down? Down. She's in free fall. The bungee cord is slack. It can't exert any force up while she's falling. Okay? Once the bungee cord takes up, okay, especially when it's stretched its maximum amount at that very bottom point where her velocity is 0, okay, all of her acceleration is which way? When she's stretched the cord as much as it can go, she's accelerating up. She has to be. If she wasn't, she wouldn't slow down to a stop. Okay? So as soon as that cord takes up and starts to stretch, she's now accelerating upwards. She's still moving downwards, but she's accelerating upwards. Okay? And she'll continue to do that until gravity begins to pull her back down. Okay? That's why you oscillate up and down a little bit after a bungee jump. Okay. That's all we need with that. Okay, so now we want to talk about systems. Okay? Systems are situations where you have multiple forces and multiple masses. Okay, so the system has many parts. That's the definition of a system, something with many parts. Okay, so now we're looking at this system consisting of 2 blocks. Okay, a 20 kilogram block and a 10 kilogram block, and they're connected by a light rope or a string. Okay, so 2 blocks of identical material are connected by a light rope on a level surface. Okay, an applied force of 55 newtons to the right causes the blocks to accelerate. While in motion, the magnitude of the force of friction on the block system is 44.1 newtons. Calculate the acceleration of the blocks. Okay, here's what we have to look at. Is there any way for the 2 parts of this system to accelerate at different rates given that situation? No. They're connected. Okay? If they don't accelerate at the same rate, either the back block falls off or catches up to the front block. And that can't happen if I'm pulling it at a constant rate. Okay, if I'm giving it just a constant force, it's going to accelerate towards me. But the 2 parts have to have the same acceleration because one is pulling the other. Okay, if one is pulling the other can't accelerate at a rate different from the one pulling it. Okay, it would be like if you were towing a trailer with a truck and suddenly the trailer passes you. You can't do that. I mean, it could if you jackknifed, if you slammed on the brakes, but that's a different situation. But while you're just towing, okay, while you're just accelerating, the trailer isn't gonna pass you. And it's not gonna fall away from you either, okay? It's always going to accelerate at the same rate as the thing that's pulling, okay? It has to because they're connected. Two connected objects in a system have to have the same acceleration, okay? Now, if they have the same acceleration, are they real, do I have to consider them as two separate masses? Nope. I can consider them to be one mass. Okay? I could deal with them individually if I wanted to, but in this situation, it makes more sense to just deal with them as one 30-kilogram object. And the reason for that is, they told me the amount of friction acting on the whole system, not on the 20-kilogram block, not on the 10-kilogram block, but on the whole system. Okay? So what I would do is I would, right off the bat, simplify my free body diagram. And this is like the most important step in solving a system question. And that is recognizing that all the parts have the same acceleration. So they're really one mass. That's really what's going on here. I have 30 kilograms worth of mass being pulled forwards by a 55 Newton force and backwards by a 44.1 Newton force. That's really what's going on here. Yes, it's actually a 20 and a 10, but it doesn't matter. They're moving together. Okay? All right. I want to calculate the acceleration of the blocks. So net force equals mass times acceleration. Do I have what I need here? Well, I still have to calculate what? The net force. Okay, so 55 minus 44.1. Okay, sorry, this should also say vector sum, right? Okay, so mass times acceleration is going to equal 55 plus negative 44.1, which should be 10.9, right? So now that I have that number, and I know the mass is 30 kilograms, I can calculate the acceleration of the blocks. Oops, 30 on the top. Okay, so acceleration is going to be F net divided by mass. Okay, so that's going to be 10.9 newtons divided by 30 kilograms. Okay, so the acceleration of these blocks is 0.36 meters per second squared forward. Now, here's how I would have written that question, just to make it a tiny bit trickier. It wouldn't change any of the math we just did. I just changed the wording to this. What's the acceleration of the 10-kilogram block? It doesn't change any of the math, and it doesn't change the answer either. But what will a lot of people do? Make the mass 10. As soon as I say calculate the acceleration of the 10-kilogram block, everybody gets focused on the 10-kilogram block and forgets this is a system. And all parts of the system affect the system and accelerate at the same rate. They would forget right away that they still have to use the entire mass of the system in this question. And all I do is change like one word in the question. What's the acceleration of the 10-kilogram block instead of the system? Okay? And right away it catches people. Oh, I just showed you one more of the tricks in my bag of tricks. You know, that one that doesn't have many tricks in it. Okay. All right. Let's have you guys try number 1. Okay, the bucket of nails question here. Okay, so you got 2 buckets of nails. Okay, and they're hung one above the other and pulled up to a roof by a rope. Each bucket has a mass of 5 kilograms. The tension in the rope connecting the buckets is 60 newtons. Calculate the acceleration of the buckets. So this is both a system question and an elevator question. Okay, you're going to use a little bit of both. And it also kind of has the trick I just showed you in it too. So, to do the 2 bucket question, you have to remember that a system may be a combined set of masses that accelerate at the same rate, but it's also 2 separate masses that accelerate at the same rate, which means I can use both pieces to solve the question together, or each of them individually to solve for the answer to a question. And that's what I have to do here. I may in fact have a 5 kilogram bucket being pulled upwards by an unknown force, okay? But I also have that bucket connected to another bucket. And I know that the force on the bottom bucket upwards is 60 newtons, because that's the force they tell me. The force or the tension in the rope connecting the 2 buckets is 60 newtons. So, how much force is acting down on this bucket? Or what force is acting down on that bucket? Gravity. Can I calculate how much gravity is acting on the bottom bucket? Yeah. Okay. I'm just going to go force of gravity equals m times g. 5 times 9.81 is 49.05 newtons. Okay. Can I calculate the net force on the bottom bucket? I know how much is pulling up and how much is pulling down on the bottom bucket. Can I calculate the net force on just the bottom bucket? Yeah. Could I use that to calculate the acceleration of the bottom bucket? And since the bottom bucket and the top bucket are in the same system, their accelerations have to be the same. Okay? So I can calculate the acceleration of the system by calculating the acceleration of any single part of it as well. Okay? So the one we did before was use the whole system together and solve for this. But we also have to recognize that because everything in a system accelerates at the same rate, I can use isolated parts of a system to calculate information about the whole system as well. Okay? And that's what we're doing here. So the net force on the bottom bucket, okay, will be 60 newtons minus 49.05 newtons. Okay, so that's going to be 10.95 newtons. Okay, that's the net force on the bottom bucket. Okay, since I know the mass of the bottom bucket, I can calculate its acceleration. So 10.95 over 5 gives me the acceleration of the bottom bucket at 2.2 meters per second squared up. Okay? Everybody all right with that? No? Okay, where'd I lose you?
Last question you said we were not to use like part of the equation to figure out, and then you did that, and I was like, how?
Okay, I don't think I said you weren't allowed. I said in this one, you need to use the whole system. Okay, so in the previous question, this one here, I needed to combine the masses because the information they gave me was a combined force on the whole system. Does that make sense? In this one, they told me pieces of the system. They said, here's a force that acts on just this part, and here's a force that acts on just this part. So then I went, okay, I'll use that part and extrapolate to the whole system. Okay? Whereas on this one, we did the opposite, right? And I even said at the end, I would reword this to be just the 10 kilogram block. Well, then I'd say, oh, well, this applies to just one part of it too. So, yeah. All right, so now the second question involves using the information from that first one we just did. Now they're saying the force of friction on the 10 kilogram block, so just the 10 kilogram block, has a magnitude of 14.7 newtons. Calculate the tension in the rope that's connecting the 2 blocks. Okay? So my advice would be this. All the information you have from the first time we did this question is still applicable. Okay? So we still know this force here is 55 newtons. Okay? We still know the total frictional force on the whole system is 44.1 newtons. Okay, that still applies as well. Okay. Now they've just put one extra thing in. They want to know what is the force acting backwards between, basically what's the force of the 20 kilogram block pulling on the 10 kilogram block? That's what they want to know. What's the tension in that rope that connects the two blocks? Okay. They've also told you that the force of friction on the 10 kilogram block, okay, is 14.7 newtons. Okay, so you're looking for that force right there. The other thing that we calculated in the last question, the acceleration, also still applies. Okay, so we still know the acceleration from the last question, and it was 0.36. Okay, so all that information is still in play, but now we want to know what the tension in the rope between the two blocks is. Okay? My suggestion is to use the first block to calculate that, but you could use the second block as well. It can be done either way. There isn't a better choice. Either one is equally good. All right, so I'm going to use the 10 kilogram block to solve this. Okay? The forces acting on the 10 kilogram block are the force of friction, 14.7 newtons that they told me, the force of the 20 kilogram block pulling back on it, which is tension in the rope, okay? And the force of the hand pulling it forward, 55 newtons. Okay? Now, right now, I know the mass of the block and I know the acceleration of the block. What can I calculate with those two numbers? What does mass times acceleration calculate? Ooh, boy, we need to know that. It's like, it is Newton's second law. Right? I can calculate the net force on an object by going mass times the acceleration of the object. Everybody with me there? And the other way I calculate that is the vector sum of all forces. And I use both in pretty much every question I do. Okay? But for right now, I'm going to use this part. I'm going to take the mass, 10 kilograms, multiply by the acceleration, 0.36, and know that okay, my net force is 3.6 newtons forward. Okay? That's my net force. Now I'm going to go back to my free body diagram and do this. F net is the vector sum of all forces. That would be the force applied, that's going to be the hand, plus the force of friction, the 14.7, plus the tension in the rope between the boxes. Okay, those are the three forces that add up to my net force, and they add up to 3.6 newtons forward. Okay, so I only have this one to find because I know the force of friction, I know the applied force, and I know the net force. Okay, so I'm going to manipulate so that I've got the tensional force by itself. In other words, I'm going to subtract these two forces over. Right? So F net minus the applied force minus the force of friction will give me the tension in the rope connecting the boxes. Everybody follow my logic there? Ashley's looking at me. Where did I lose you?
I have no clue what's going on right now.
Okay, let me just go back. Right? The hand here is pulling these two boxes. Right? They're connected by a rope. Okay? So if I'm walking along and I just have a rope dragging on the ground, it's pretty easy for me to walk, right? But if I connect that to something else, does it suddenly become harder to walk? Okay, because once I connect something else, it pulls back on me when I pull forward. So that's the force we're looking for, is that force that's in the rope, that's resisting here. Okay, so what they've told me is that the 10 kilogram block has a force of friction dragging against the floor of 14.7 and the force of the block behind it pulling back as well. Okay, and then there's my force pulling forwards. Okay with that? Okay. From there, because I know this force, and I know this force, and I know the acceleration of this block, I can calculate the force I don't have. Because net force is mass times acceleration. And it's the sum of all the forces acting on the block. Okay? There's always two ways to calculate net force.
Why did you use the 10 kilograms then?
I can use either one. The answer is I could use either one. I chose to use the 10 first. I'm going to show you the 20 as well. If you solve it with the 20, you'll get the same answer if you did it right. Okay. All right, so back to this now. Okay, I've got my net force minus this minus that equals the tensional force. So 3.6 newtons forwards, so positive 3.6, minus 55, that's the forward force, minus negative 14.7, because the force of friction is backwards, okay, will give me the only force I didn't know before, the tensional force. So we have 3.6 minus 55 minus negative 14.7. Okay, so there's the force between the boxes. Okay, and it's negative because it's resisting the 10 kilogram box. Now, if I do this from the perspective of the 20 kilogram box, that number will come out to be positive. Because from the 20 kilogram box's perspective, that's a forward force. Okay, so tomorrow, because we're going to run out of time here, okay, I will show you how to calculate that with the 20 kilogram box. Okay, basically you use what's left of the friction, so 44.1 minus the 14.7, and that's your only force backwards, and then you go from there, right? Is that how you do that? You get the same number?
I didn't know this.
Okay,
So long.
we'll look at it tomorrow. Don't panic, it's early still. Okay? This is about as tricky as they get.